So here we have a thermoelectric generator. You could see it in the middle. This device can convert heat into electricity. One side has to be hot and the other side has to be cold. So let me go ahead and demonstrate that for you. So here we have the thermoelectric generator in its active state. On the left side, the cup contains hot water, and on the right side it has cold water, which you could see by the ice cubes. The thermoelectric generator, which is sandwiched in between the two metal plates, converts heat into electricity. As heat flows from the hot side to the cold side, some of that energy is converted into electricity, which powers the motor. Now let's talk about the thermodynamics behind these devices, the thermoelectric generators. I looked it up online and the typical efficiency is around 5 to 8%. So let's go with 5%. So what does that mean? Efficiency is equal to the work done divided by QH, where QH is the energy flow from the hot reservoir. So let's say 1,000 joules of energy per second is traveling from the hot reservoir. About 5% of that thermal energy will be converted into useful work. 5% of 1,000 is 50. So about 50 joules will be converted into electrical energy that could be used to spin the motor. The other 950 is the thermal energy that's lost. Most of it will be lost to the cold water solution. Some of it could be lost to the environment, but that's just the energy that we didn't capture. So another way of seeing it is using this diagram, TEG, which stands for thermoelectric generators. So we have 1,000 joules of energy coming from the hot water solution, and 950 is lost to the environment. So the other 50 joules, as we can see in the circuit diagram, is used to get the motor moving. So that's the thermodynamics behind these type of devices. They're not very efficient, but they do work. Now here's a picture of the thermoelectric generator. It basically looks like a flat rectangle. And if you want to see a picture of it, an actual picture, you can go to Google Images and just type in thermoelectric generators and you'll see it there. Now, the red wire is the positive terminal of the TEG, and the black wire is the negative terminal. But because I have a black background, I can't really draw a black wire here, so I replaced it with a blue one. Now, what's going to happen if, instead of trying to generate electricity from the TEG, what if we put electricity into it? So what if we reverse the operation of this device? What's going to happen? This device becomes kind of like a heat pump. What happens is it begins to pull heat from one surface up into the other surface. So when electricity is flowing through this device, that's the direction of conventional current. Electrons flow in the opposite direction. But once we have a current flowing through this device, heat will be pumped from one side of the device to the other side. So in this illustration, the bottom part is going to become cold, while the top part will become hot. So you can create a temperature differential by applying an electric current to this device. And you can test it out, but you may need a large or relatively large current flowing through this device to see a significant difference in temperature. Now, there's one important thing I do want to mention, because you don't want to have too much current flowing in this device. A large current can create a fire. It can cause this object to burn, and that could become a safety issue, so you don't want to do that. It may be wise to use a current limiting resistor to prevent too much current from flowing into it. So just a safety detail that you want to take into account. Now let's briefly spend a few minutes talking about the operation of these TEGs. As heat flows from hot to cold, electrons, they flow from the hot side to the cold side through the N-type semiconductor. In the P-type semiconductor, electron flow is in the opposite direction. But in the P-type semiconductor, the mobile charge carriers are holes, whereas in the N-type semiconductor, the mobile charge carriers are electrons. The holes move in the opposite direction of electron flow. So in the p-type semiconductor, the holes are moving from the hot side to the cold side, whereas the electrons are moving in the opposite side. The positive terminal is the part that is connected to the p-type semiconductor. The negative terminal is the part that is connected to the n-type semiconductor. Conventional current flows from the positive terminal to the negative terminal, but electron flow is in the other direction. But for this example, we're going to focus on electron flow. So I'm going to draw one continuous arrow so you could see how electrons flow throughout this circuit. So starting from the hot side, it's going to flow down through the n-type semiconductor, through the wire, through the voltmeter, and it's going to travel this way, up through the p-type semiconductor, through the metal conductor that connects the n and the p, and then it's going to just flow in that continuous direction. So that's how the electrons are flowing in the circuit. But just remember, in the p-type semiconductor, the holes are the mobile charge carriers. I just want to simplify this diagram and the working principle behind it. So that's it for this video. Hopefully you found it to be helpful and educational. Thanks again for watching.